Okay, engineers, on this video we are going to see the convolution theorem. What we are going to see is, I have to say, it's a very ugly and nasty operation. Convolution is actually an operation, just like multiplication, addition, or division. All right. So the symbol of the operation convolution is like this, and the definition of convolution is f of t convolution with g of t is equal to the integral from 0 to t of f of tau times g of t minus tau, and that's it. All right. Okay, let's see one example. Let's say that f of t is equal to the exponential of t and g of t is equal to the sine of t. Okay. Now, if we do f of t convolution times g of t, it's not times, it's just f of t convolution with g of t, which is exponential of t convolution with sine of t. Okay, what we have to do is the integral from 0 to t of exponential of tau. You replace here by tau, and then sine of t minus tau, differential of tau. Okay. Now, this is a very complex integral. Actually, is very long, so I'm going to skip the steps. If you develop this integral, you will get the following. You are going to get 1/2 of exponential of t minus the sine of t minus the cosine of t. That will be the result of making this integral. Again, it's a very long procedure. I don't want to get lost in the procedure of making the convolution. Now, I have to tell you, making the convolution is a very painful procedure. Okay, now, the result of this, you have to believe me. So here I'm going to make, I believe, in the professor. I believe the professor. Okay, now, what I want you to focus is on this characteristic, and this is why we are going to see the convolution theorem. What will be the Laplace transform of this exponential of t convolution with the sine of t? Okay, it will be 1/2 of, because the result of this convolution is this, then is the same as making the Laplace transform of this result. The Laplace transform of the exponential of t minus the Laplace transform of the sine of t minus the Laplace transform of the cosine of t. Okay. Okay, let's continue. 1/2 of the Laplace transform of the exponential is 1 over s minus 1. Okay. And then minus the Laplace transform of this is going to be 1 over s squared plus 1. The Laplace transform of the cosine is going to be minus s over s squared plus 1. Okay, let's do common denominator here. 1/2 times the common denominator is going to be s minus 1 times s squared plus 1, because this s squared is actually the same. So if we do the common denominator, then this divided by this is going to be times 1. Is just going to be s squared plus 1. That's it. And then this divided by this minus s minus 1. This divided by this, and then times s minus 1 times 1 s minus 1, and then minus s times s minus 1. If you make the division of this divided by this, s minus 1 times s. Okay, so 1/2 of s squared minus, no, plus 1, and then minus s here, and then plus 1, and then minus s squared plus 1. Okay? Yes, plus 1, okay. Divided by s minus 1, s squared plus 1. Okay. Anything cancels? Yes, actually. This and this cancels. Sorry, my mistake here, it is plus s. minus s squared plus s. Okay. And actually, the s also cancels. This and this cancels. So what is left? 1 plus 1 is equal to 2, so it's equal to 1/2 times 2 divided by s minus 1 and s squared plus 1. So actually the 2 cancels, okay? So the only thing left is 1 over s minus 1 and then s squared plus 1. Now, remember from where we get this. We get this from the Laplace transform of the exponential of t, convolution with the sine of t. Now this is why this is very important. Now if you split this or just make a simple separation, it's going to be 1 over s minus 1 times 1 over s squared plus 1. As you can see, we haven't modified anything here, but you can see here this is the Laplace transform of exponential of t times the Laplace transform of the sine of t. Looks like the Laplace transform of the convolution in the time domain is just a simple multiplication on the s domain. So you don't have to go through the convolution and then apply the Laplace transform. All you have to do is that if you have the Laplace transform of the exponential convolution with the sine, all you have to do is multiply the exponential the Laplace transform of the exponential times the Laplace transform of the sine of t. Now, looks like it is a simple multiplication. But is it true? It always happens like that? Well, the answer is yes, engineers. And this is why we see the convolution on the Laplace transform. It turns out that the Laplace transform of f of t convolution with g of t is simple f of s times g of s, or the other way around, the Laplace transform of f of t times the Laplace transform of g of t. Now, this is the convolution theorem. Okay, now, we have to demonstrate that this actually happens, because what if this is only, we were lucky on this one. We have to prove that it happens every time, alright? But this, well, we will see the demonstration on the next video. It's going to be very long, but we are going to see it. See you in the next video.